your audio. Good morning, everybody. Can you hear me at home? Thank you. Cool. Sorry, I'm a little late. Let me grab something and we'll get started. So we're going to be talking, so we'll see if there are any questions about other things. And then we'll be talking today about chapter 16. So we got 5 days left of class. And we have, I'd like to do a bit of chapter 16 because I think that's cool and important. Let's see, meeting list, start. There we go. And if there's time, we might do a bit of chapter 17 as well. It's less clear to me how that's going to play out. It'd be nice to do some of it, but I don't know. We'll see how things go. Let's see. Desktop. There is a quiz on Canvas set for, it's due on Thursday night, and it is like the other quizzes. You should have 3 goes at it, and we'll talk today about a lot of the stuff that's on that quiz. It's all stuff from chapter 16, so in theory you could just read chapter 16, it would all work. In practice, hopefully we'll be able to cover some things in class that'll help. And then I would be happy to spend all of Wednesday basically answering questions about about that assignment, about the quiz. So if you've tried things before Wednesday and come to class with questions, that would be awesome. Highly recommend. Okay, so are there questions about anything, the exams, the state of the world, anything I can help with? Okay, then we're going to go. So I'm going to share my Jess. Share screen. Jess, share. Whoa. We are not displaying on the screen here, so I need to figure out why that's happening. Guessing it's input issue on this thing. I have no idea which. The right. Hang on a sec, peeps. Input A. Does that work? Input B. That doesn't look good. Try input C. That's where we were. Oh, there we go. Okay. Sorry about that. We had to fix the projector set up so that the folks here in the room could see what was going on. So can everybody at home see the Jess? Good, thank you. So ignore grayscale for a second. Actually, I'll move it down so it's not even visible. Let's think about these 2 definitions, which are, use ideas that we talked about in some cases ages ago. We haven't done pictures in forever and ever. But no red takes a picture, loops over all the pixels in the picture, and sets the red to be 0. Okay? So this should look vaguely familiar, hopefully. Increase volume loops over the samples in the sound and sets the value of a sample to be twice the old value of the sample. So it takes the sample, gets the old value out of it, multiplies that by 2, and then sets that to be the new value of the sample. Questions about these, either of these? Now, the point here is that these look very similar. They're both, they take a thing. Now, the things are different. One's a picture and one's a sound. But they take a thing, and then what do? They get some list of things out of the thing they're given. I'm going to use the word thing a lot here, my apologies. And then they loop over all the items in that list. And for each item in the list, they take an action on that item. In one case, we set the red to 0. In the other case, we double the value. But we're going through every item in a sequence, and we are performing the same action on all of them. Okay? This is actually a remarkably common pattern in software development. You often have a lot of something, and for every one of the somethings, you need to do something. And if you think about the registration system here at the university, where there are tens of thousands of active students across all the campuses, you've got to do things like, for every student, assign them a registration time. For every student, check that their bills are paid. For every student, see if they're ready to graduate. Or maybe for every student who's declared graduation, check that they're actually gonna graduate. Like, have they actually satisfied their requirements? So there are a lot of things where we do something for every item in a list, and it's the same something. Maybe that something's got logic in it so that the actual behavior is slightly different depending on the thing, but the general concept, the algorithm, is the same for every item. So in this example, get sample value times 2. Well, let's think about set red. For set red, we literally do the same thing every time because we always set it to 0 regardless of what it was. In get sample value, in the picture one, what we do depends on the value of the sample, right? So at some level, it's the same. We double it, whatever it is. At a lower, more detailed level, it varies because it depends on the actual sample. If it was 10, it becomes 20. If it was 100, it becomes 200, right? So, but we apply the same logic every time. That's the important thing, okay? And one way to see that, let's bring our grayscale friend back up into the picture. Go up a little bit. Oh, come on, behave. There we go. So here's grayscale. Again, we're going over every pixel in a picture, and we're doing something to all of them. The something is a lot more complicated than it was when we just set the red to be 0 up here, but still, there is an algorithm that we are applying to every pixel, okay? It's the same algorithm that we apply to every pixel. It's just a more complicated algorithm than setting the red to 0. And we can see that a little more easily if, as my comment tells us to do here, we pull this out into its own function. So if I copy, I'll cut this. Def grayscale pixel, boom. And now everybody's indented a little more than they need to be. So let me clean that up. So now, if I just call grayscale pixel. Now this looks much more like the things we saw above. We've got a function definition, it takes a thing, we get some sequence of things out of it, we loop over the items in that sequence, and we call some function. We apply some action to every one of the pixels. And that's more or less the same as here. We loop over everything, apply some action to every pixel. Here, we apply some action to every sample. And we can make this similarity even more explicit by actually turning things like this into their own functions and things like this into their own functions. Okay. Questions as I sort of pull these pieces out? We've been moving pretty fast. If there are questions, definitely holler. Okay, so we'll say 0 red pixel set red pixel 0. Oops, hit the wrong button. And so then this becomes 0 red pixel. And then here we can extract this. Oh, undo. Double sample value. And, you know, we've got this as one longish line because I was trying to make the similarity clearer earlier. Now that we've pulled it out, there's no reason we couldn't say, stretch it out a little bit, which might make it a little more readable. I mean, this depends on how you feel about things. Oh, we could even be like new value equals 2 times, ooh, we could call it old value. Really exciting. And this would be new value. So, you know, we can expand that a little bit if we find that that's more readable. But the important piece is, again, we get these guys together. Wow. Boom. And now. Boom. So now that we've extracted functions, these are really very much the same. Every one of these definitions, no red, increased volume, and grayscale, takes a thing, extracts some collection from it, loops over that collection, and calls a function on every element of the collection, right? There is a very similar structure to all of these. Does that make sense? Are there questions about that? Because that's really a very critical observation. The whole rest of this doesn't make a lot of sense if we, you know, if we're not clear on sort of the idea that these are very much the same. Questions? Julio? Okay. Then, in computer science, I mean, one of the things that we really want to try to avoid is repeated logic. Whenever we find ourselves doing the same thing over and over again, that's a bad sign, and we'd like to find a way to make it go away. Because if we're repeating ourselves, if we repeat ourselves incorrectly, then we propagate the mistake. Like if you misspell a word in a paper and then you copy and paste that word 6 other places, now that misspelling is all over the place. And when you want to try to find it and fix it, you got to find all the instances of it, which with a modern word processor, frankly, isn't all that hard. But if you imagine having to do it sort of on a typed document, it would be a lot more difficult. So we don't like repeating stuff if we can help it. And this is sort of one of the great mantras of computing, arguably. And Python gives us a tool to do exactly this. And it looks like the following. So we can say, instead of no red, I'll call it no red FP. And here FP stands for functional programming. So I'll explain why we would use that word in a second. Map 0 red pixel get pixels. Oops. Picture. That's the whole function. So what is going on here? So map is a built-in Python function. So this is Python, not Jest. So any Python system would have this. And it takes a function as its first argument. Now this is a slightly weird idea. We've always passed around numbers or pictures or sounds as the things that we give to functions. Here we're giving a function to a function, okay? It's a bit like handing an assistant to another person in the organization and saying, this person now works for you. They will do stuff on your behalf. Which if you stretch that analogy too much gets creepy, but we're not going to go there right now. So we are passing a function, 0 red pixel, which was up here. And so I'll move it down so it's closer to our friend. So we can see them together. Zero red pixel. So this passes this function, and it's just a function, right? There's no parenthesis after the name. We're not calling it with any arguments. We are literally just passing the name of the function as an argument to map. This is a pretty weird idea, okay? And for a lot of people, it almost seems like it shouldn't be possible when you first see it. But actually, it's a very powerful tool. The idea that functions are things that you can pass around, and in fact, you can return them. You can write functions that create functions and pass them back. We're not going to get into anything that fancy, but that is, you can do that in Python. So we can write functions that take functions as arguments. We can write functions that return functions as values. Functions are what are called first-class objects. They're things we can act with, just like we can act with integers and floats and sounds and pictures. Not all programming languages have this property. So in Java, for example, functions aren't really the same as other values. They've made a bunch of changes in Java in the past decade that have made it more possible to do this kind of thing easily. But certainly in the early days, Java was very much not like this. But a lot of more modern languages tend to allow this kind of behavior. And we call this functional programming because we're able to pass functions around as objects. Okay? And so map takes a function and a sequence of some sort, and it applies this function to every item in this sequence. Now let's actually, before we get into the pictures, let's look at this in a slightly, I started at a very high level, like complicated things like pictures. Let's actually look at this in a simpler form. Let's define like double and triple. Okay, just so that we have a couple of things to work with. What have I done? Oh, I didn't def it. Yeah, good catch. Thank you. Oh, and I didn't put a colon at the end of that. Okay. Whew. So double 7. Well, not double ampersand. That's not going to work. Triple 7. Okay. So we can say map double and we get twice every number in the list that I handed it. So it took this function and applied it one at a time to each of the values in this list. And if you had to write a function that took a list and doubled everything, you'd have a for loop that goes over each item in the list and you do the doubling, right? And map is just doing that for you. So that triples everything. And we can do things like, you know, range of 20 is 0 to 19. This is 3 times every one of those values. Okay? And so map's been there all along, and actually an awful lot of what you've done with sounds and pictures, you could have probably done with map, and not had to write all those for loops that you've been writing for weeks and weeks and weeks. Oh, sorry. Yeah, so map actually would do a lot of that stuff for us. Okay? And we can use it. Let's actually load up a picture. Make picture, pick a file. Where are Dogstools? There's Dogstool. Oh, actually, let me share my whole screen because that'll work better here. Since we're going to actually manipulate pictures for a second. Yeah. So we can say show Dogstool. Yeah, so there it is. Happy day, Dogstool. Now we can say, make sure I get the right name. No red FP. No red FP. Dogstool. Show Dogstool. And lo and behold, we've removed all the red. So it mapped over every pixel, and it set the red value for every pixel to 0, which darkened the image and left us with blue and green. So we get a very sort of turquoisey picture at the end. So like this real strong white here is now this bluey green because the red's been removed, and all that's left is the blue and the green. Doesn't have that much effect on the sky because that didn't have very much red in it to begin with. Okay? Questions about that? Yes?
All right, so using map as a function sufficient enough to replace for loop?
So Joseph's question is map sufficient to replace all for loops? So I think you're probably, you know, I haven't thought about that question, so I don't want to sound too confident, but I think you're probably right. I think you might be able to replace all for loops. Well, so I'm going to say I don't know for 100% sure. I think it would be capable of replacing very nearly all for loops, and it might be able to replace all of them. But one thing I hadn't really thought about until you asked the question is a for loop guarantees that you will process the items in the sequence one at a time, left to right. I think map also guarantees that, but I'm not 100% sure, because one of the things that you might do in some systems, but I don't think Python does this, and this is why I'm being a little hesitant. In some systems with map, you might actually introduce parallelism to speed things up. So if I know I've got 100 things to process, okay, and there's 4 of us here in the room, I could say, Zeke, you get 25 of them. Joseph, you get 25 of them. Sophie, you get 25 of them. I'll take 25 of them. Let's all work in parallel, and then we'll bring it back together again at the end. And in some systems, and like I said, I don't think Python does this, but I don't know for sure because I've never looked into it. In some systems, map gives you the potential to do that kind of thing in parallel. It will actually split up the work and let different cores on your computer do them in parallel. Whereas I know a for loop won't do that. And this could be important because in a for loop, if you're doing something where the action on the 12th item depends on the first 11 having been already finished, then parallelism would break that. Because Zeke might be working on the first item, and Sophie might be working on the second item, and I might be working on the third item at the same time that you're working on the fourth item. And if you were depending on us already being done, that's going to break. So there could be some subtle differences. But I think in the vast majority of cases, if not all cases, you're correct. I think you could take any for loop and probably replace it with a map. And so a for loop in some sense is a convenience, not a necessity. Another way to look at it is you could say a map could be implemented with a for loop, and the map is the convenience, and the for loop was the necessity, right? So you could pick either one of them to be the fundamental building block and build the other one out of it. But it wouldn't really matter which order you did things in. So, does that make sense? Cool. Great question. Other questions? Zeke.
So red zero pixel creates a pixel, and get pixels of picture is a series of pixels.
Right. And if the types were wrong, you'd have a problem. So if we try to do, let's say map zero red pixel across the list we get an error. So input is not a pixel in set red. So map called zero red pixel, which called set red, and it tried to set the red of 5 to be 0, and it said 5 is not a pixel, and I am sad, okay? And in the same way, if we tried to say map double across, oh, actually, this might work. Might not blow up, yeah, because times 2 does that with characters, does that doubling thing. So it took M times 2 and got 2 M's, and O times 2 and got 2 O's, and R times, yeah, so, but if we had, I don't think you can add 1 to a string, so if we had like def add 10, and then we said map add 10 across a string, I think that'll fail, yeah. Because it can't do plus and M, doesn't know what to do. So that failed. So yes, the type of the elements in the sequence have to be the correct thing to be an input to the function that you pass in. And if the function takes a thing of type X and gives you back a thing of type Y, then you have to hand map a list of X's and it will give you back a list of Y's. So, okay. So as an example of that, if we said map len, it is len, right? Len Morris. Yeah. Map len University of Minnesota. So len takes a string as an input and returns a number as an output. So when we map with len, we take a list of strings as an input and we get a list of numbers as an output. So you can infer things about the types by looking at what the function does. Will tell you kind of what kinds of things need to be in the list and what kinds of things would be in the result. And one thing that this suggests, which we had not actually done anything with, map here actually returns a list of pixels, a very long list of pixels, because there's going to be hundreds, thousands of pixels in the image. We didn't return it, like there's no return word here, so that list of pixels just fell on the floor and was lost. But because in this case, 0 red pixel modified every pixel in place, the picture is still changed when we go back and look at it. And we never needed the list of pixels that got generated. But if we had needed it, we could have returned it. We just didn't need to in this instance. Questions? Any questions at home? We good? Any other questions here? Excellent questions so far. Sophie. No, apply is not the same thing as map. So I'm actually not sure why they start with apply. I mean, I think they're just trying to point out that apply exists and to make this, they'll make this point that you can pass functions around as arguments. So apply, oops. Doing this from memory, yes. So apply takes a function and a list, which are the arguments to that function. And it applies that function to the arguments in the list. Now here, double only took one argument. Let's make an example where we have many arguments. So let's see. Let's have a function where we take 3 items and we return their average. Now, so average 3, if we give it 5, 8, and 9, gives us 7. And that's an integer because we're doing divide by 3, not 3.0, so it did the rounding thing. Now, if we say apply average 3, then how do we say it takes 3 arguments? We do that by putting them in a list. And so that says this is going to be the same effectively as this here. So the list here is not a list like we saw in map. We're not taking the function and applying it to each item one at a time. We're taking all of those things and as a group saying they are the arguments to the function. Okay. And you're actually unlikely to ever use apply, which is what part of the reason it's a little weird that they open with it in the book. Apply is important, actually, and if you get into some more advanced stuff, apply is really very significant. But here now, in the things you're doing, you are not likely to ever use apply. So don't let the fact that the book opens with apply distract you too much. But it's a great question because it does feel like that this looks like map, right? It looks a lot like map. And you could easily, assume that they're the same or at least related. But apply is using the list here to collect a set of arguments that are passed as a group to the function. Here, this is a collection of values that the function will be applied to one at a time for as many times as necessary to get through the whole list. So with apply, the function is only called once. With map, the function is called n times, where the n is the length of the list of values that we pass it as the second argument. So that's a really good question. Thank you. Other questions? Okay. I'm actually going to switch back to just, well, no, actually I won't, because we will want to pop things up quick. So I'm going to go back and find, okay, there's my no FP. So here we could say increase volume FP. We could do a functional version of this, and that would be map double volume get samples from sound. And here we're going to call grayscale pixel map grayscale pixel get pixels picture. Oh, and I should have said FP there. FP, just to make it different from the previous one. So these all now do the same thing as our earlier version, but they all do it with map. And we didn't have to write an explicit for loop. We didn't have to name an index variable. We didn't have to worry about how the name of that index variable would interact with other things. Notice we didn't have to give a name here to the list of pixels or samples. By just calling get samples or get pixels, we're passing that list in, but we never had to come up with a name for it. We never had to have a name for the pixel or the sample, an index variable in the for loop. So we get to avoid a bunch of naming. And naming is actually a pain in the butt. It's nice not having to name things. So this is pretty slick. Okay. And so if we load this, we ought to be able to do things like, let's say, anti is make sound, pick a file, and back up again. Oh no, I didn't want to back up that far. We want to do in here. Oh, there's media sources. Anti-disestablishmentarianism. Oh no, it's Anthony. There's anti-disestablishmentarianism. So if we explore that, see what it looks like. And then if we say increase volume FP anti, whoa, what did I do wrong? Double volume. Oh, it's probably not double volume. It's probably double sample volume or something. Double sample value. Wow. Double sample value. This is why names are pain. You forget them. You know, and I only typed that like seconds ago and I couldn't remember it. If we explore the current version of anti, we have clearly cranked up the volume. Right? So even without playing them, it's obvious that the new one is considerably louder than the old one. So if we play it, oh, the volume on this laptop has been set to 0. If anybody at home has been trying to talk and I've ignored you, it's because I'm a terrible person and I couldn't hear you.
Anti-disestablishmentarianism.
Versus, hello. Come on, why won't you let me? Oh, it's tucked behind the, oh, heavens, Betsy. There we go. So,
anti-disestablishmentarianism.
That's the quiet version and the loud version.
Anti-disestablishmentarianism.
Definitely louder. Okay. So if somebody at home has been trying to talk and I have failed to hear you, I apologize profusely. Definitely speak up and ask your question. And I'm sorry. Anybody home? Got a question? I need to be better about checking the mic or the volume on this. My apologies. Okay, so that increases the sound. And then if we want to grayscale a picture, dog stool again, show dog stool. Yeah, so it works. And then we'll grayscale FP, dog stool. Grayscale, voila. And one thing that's kind of nifty about this is notice that all the logic about taking a pixel and making it grayscale is now embedded in a single function. And if we need grayscaling in multiple places for different reasons, we can have all of those call this function so that we don't have to repeat this logic in other places. And if you remember all the way back to this part of the book, this is the simplistic version of grayscale that ignores the fact that we don't perceive red, green, and blue equally. And there's the fancier version in the book that multiplies them by sort of odd constants. And I didn't do that here because I was lazy. And I just figured out, I was just trying to make an example. But now, if we had a bunch of code that called grayscale pixel, if we decided to spiff this up and use the new stuff, all of that other code would benefit from that improvement at one point, instead of having to go find all the places where we had done this sort of simplistic grayscale and modify all of them. So that's actually really, very nice. And so we've kind of extracted the grayscalingness out of the problem and separated it from the question of doing something to every pixel. So now here, this has the do something to every pixel part, and then the grayscaling is all off in this guy here, which is really very slick. Questions about map? Map is cool. I like map. Anybody home got a question? We good? Thumbs up? Joseph's got a question.
So I have a question on the use of the return statement.
Sure.
So when I use a return statement in code itself, it can break the processing, right?
Yep.
So how can we use that in map, or is it possible to break it?
Good question. So Joseph's question is if you have a for loop and you have a return, you can stop processing early. So a return sort of breaks out of the function regardless of where you are. And so then the question is, can you do that in map? And maybe this is an example where a map and a for loop aren't identical, because there isn't a way that I know of to do that in a map. Map is going to apply the function to every item. There's not a way to say jump out early, because we've got returns here, but those returns just end the little function being mapped. They don't have any impact on the map outside of that. And there's not a way that I can think of saying end early inside of map. We'll see a thing called filter, maybe in a second, depending on whether there are questions, that you would use if you wanted to stop early. It would be one way to do that, is combine filter and map. But a map by itself is going to do all of them whether you like it or not, unless one of them generates an error. So if we have, let's say, def reciprocal, I don't know if that's actually spelled right. So we're going to return 1 over x. And if I say map reciprocal 1, 2, 3, oh, that's kind of boring. Let's make this 1.0. We can actually see some stuff. Okay, 1, 1/2, and 1/3. Now, if I say map reciprocal 1, 2, 0, 3, 4, 5 will blow up because we tried to divide by 0. But notice it's not like, I mean, it did actually do the first two, but we don't have any access to those values. The fact that it did 1/1 and 1/2 and got 1.0 and 0.5, that's lost to us. It just tipped over. So this is not a useful way to stop map in the middle. It will stop map in the middle, but there's not much that you can do with it that would have been helpful. So that's actually a great question. And I think it means that would be a difference between map and for, and that you can leave for early and you can't leave a map early. Other questions? Good? Okie dokie. So we'll take that as a lead in, and we'll talk about filter a little bit. So filter and map actually go together in really useful ways. Filter takes a list, and instead of an action that is applied to every list, it is given a test that is used to check things in the list. And you keep the things that make the test true, and you lose the things that make the test false. So if we say def positive, okay, then a filter 5, 8, -9, -6, 3, -2, 0, -7, 12. So it went through that list. It called positive on every one of the items. And if positive returned true, then it kept the value. And if positive returned false, it got rid of the value. So we got 5 and 8, skipped 9 and -9 and -6, kept 3, skipped -2, skipped 0, because 0 is not greater than 0, it's equal to 0, those are different things. Skipped -7 and kept 12. And so if you wanted to only do part of a list with map, which would be one reason you might want to break out of a for loop early, one way you might do that is use filter to shorten the list first and then map on the result. So we could say map double filter positive. Oops, man. 5, 8, -9, -6, 3, -2, 0, -7, 12, map. That closes filter, and that closes map. And we get 10, 16, 6, and 24. We get twice each of the things that made it through in the earlier just filter call. Cool? So we can do some fairly complicated things by combining map and filter. So for example, let's write a function very bright. Oops, that's not right. We have to get the red, the green, and the blue. oh, let's just do this. Get red pixel plus get blue pixel plus get green pixel divided by 3. So this is now the average value. So we're just taking the red, green, and the blue of the pixel and taking their average. And we'll say it's very bright if the average value is greater than 180. I'm just picking a random number. So that'll only give us back pixels that are real bright. And then if we say, if we, oh, so load, oh, and I need to save. So now, if we reload Dodgetool equals make picture, pick a file, if we say map, do we want to make it get rid of the red or make it grayscale, the bright pixels? Let's deal with the get rid of the red, because that the 0 red pixel. The grayscale might not show up because the bright ones are mostly going to be white, I think. 0, what did I say it was? And you think I could remember. 0 red pixel. 0 red pixel. Filter. Very bright. Get pixels. Dodgetool. So we're going to get the pixels out of the picture. We're going to use filter to only keep the pixels that are really bright, that have an average brightness of at least 180. And those pixels, we will make the red go to 0. And other pixels we will leave alone. So this is taking a while because filter is applying a function to every pixel. And then when that's done, oh, and actually it returned it, a very long list of pixels, because I didn't capture that. And so it actually returned that crazy long list. And it's still going. Why is it still going? You think it would be done now? Come on. Be done. There we go. Now show Dodgetool. Hello. I am probably using up most of the memory now because I printed all those nuns out. I was not smart. Go, little computer. There we go. So that took the bright pixels and removed the red from them and left the other pixels alone. So you can see that the clouds that weren't where it wasn't super bright, the clouds retained their sort of bluey white color. Where they were really bright, they turned the sort of turquoise color that the walls turn. But then these sort of terracotta colored trim pieces didn't change color. And it's a little hard to tell, but the dark shingly bits didn't change color either. So this only affected the bright parts of the picture and left the less bright parts alone. So voila. So that was slow because of going through, let's see, I'm not going to return here because I'm going to do it again, but it ran the filter all the way through, generated that very long list of pixels, and then it did the map all the way through that, and then returned this great big long list of nuns because 0 red pixel returns the value none because it doesn't return anything. And so we get this long list of nuns. So that was a little less efficient, probably, but it's a lot easier to write. It's a really neat way to write things. It's just it wasn't super performant. And there are some ways we could improve that if we cared, and that's not really our focus here, so we're not going to worry about it. But we can do this kind of combination of filtering and mapping to do some very cool stuff. Questions? And so that's the main, well, there are kind of two main themes in chapter 16, and map and filter is sort of half the chapter. And so if you feel like you kind of get those, that's great. I'm super, super happy. And we'll talk about recursion on Wednesday. There's one other thing I'll say about this, and this is a bit of a head bender, and I'm not going to expect you to necessarily fully comprehend this next part. It won't be like a big part of the final or anything like that. Map and filter will show up, so you should get those. But this next thing called lambda is less important, but I do want to mention it. The book covers it, and it's of consequence. But are there questions about any of the map filter stuff before we talk about lambda a little bit? Going. Okay. So you'll notice we ended up making a lot of little functions here. So positive, returning x greater than 0, reciprocal, returning 1 over x, triple, 3 times x, double, 2 times x. We did, add 10 was down here at the bottom. I don't know how it got separated from its friends. Let me go put it back with its buds. Control X. Undo. No. So we made all these little bitty functions. And there's actually nothing wrong with that. Actually, I think a good small function with that, well, a small function with a good name is actually a very valuable and excellent thing. But, you know, it can sometimes seem a little crazy to have to write, you know, things like double and triple. And if in different parts of your system, you're going to have multiplying by 4 and multiplying by 7, it's like, oh, do we really want a function for every little thing we might multiply by? That seems a little much. So there is a mechanism in Python, which is called lambda, which allows us to create anonymous functions. Like, really? What is that about? So we could say map double 5896320. But if we didn't want to actually make the function double, we could create it on the fly without ever actually giving it a name. So that expression, lambda x colon 2 times x, that makes an anonymous function. So lambda x colon 2 times x makes an anonymous function. And by anonymous, we mean it has no name, that takes a single input x and returns 2 times x. So this is like f of x equals 2 times x, but doesn't require a name for the function. That's pretty weird, frankly. It's really cool, and you can do some really neat stuff with it, but it's pretty weird to think about when you first see it. And I'm definitely seeing wheels crank in Joseph's head. Joseph's like thinking hard about this one. So if we have to try it, we can say map lambda. You got to learn how to spell lambda. Oh, it's being really slow. I clearly have used up a ton of memory, and now everything's going to take a month. I wonder if I should clear the command prompt. Come on, finish. Give me the terminal back. Oh, sigh. Questions about the weirdness of lambda? Well, oh, there, the computer printed the answer. Questions about the weirdness of lambda while waiting for the computer to let me have control again. And so, let's see, clear command window. So we can also use it in things like filter. So we can say filter lambda x, x times x is greater than 25. 5, 8, 9, 6, 3, 2, 0, 10, 4, minus 25, 8. So 8 squared is greater than 25, 9 squared is greater than 25, minus 25 squared is greater than 25, 8 squared is greater than 25. So it kept these values and set aside 3 squared is 9, not greater than 25, 2, 0, 4. It set those aside and kept everybody else. So we can use a lambda like this to make a test or an action on the fly really easily. And you could do everything that I did up here with these guys, you could do with lambdas. If you didn't want to actually define 0 red pixel, right, we could do dog stew, make picture, pick a file. And then we could map. Oh, this is going to return a whole bunch of nuns again. That's going to be bad. So, okay, it's 20 after. I'm going to let it go because I don't want to get sort of caught up in fighting the computer. But we could, instead of set pixel to 0 or red to 0, we could use a lambda to do that. And then we wouldn't have to have made that little function. So have a go at the quiz. Come back Wednesday with a ton of questions. The first question on the quiz is a thing called recursion, which we have not talked about. That's something we can definitely talk about on Wednesday. It's just that sort of where the first thing in the exercises was. So if you can see that and you're like, what the hell? We didn't talk about that. Feel free to just skip it or read the book and see if you can make sense of it, one of the two. And then we can talk about that on Wednesday. But definitely come Wednesday with questions about map, filter, lambda, fun and excitement. So don't freeze to death. We'll see everybody on Wednesday.